Welcome to The Explainer. So today we're tackling one of the most powerful ideas in all of mathematics, differentiation. Honestly, it's the engine behind so much of our modern world, and we're going to break down exactly how it all works.
Let's start with a couple of questions that might not seem related at all at first. So, think about your GPS. It doesn't just tell you your average speed for the trip, right? It knows your exact speed at this very second. How in the world does it do that?
Or picture this. A company is launching a new product. How do they find that perfect sweet spot, that one price that will bring in the absolute most profit? Totally different problems, right? Well, maybe not.
The answer for all of these lies in a single, absolutely brilliant mathematical tool. It's a tool designed to measure something very specific, change as it's happening at one single instant. And that tool is called differentiation. Okay, let's dive in.
So the basic problem that differentiation solves is actually pretty easy to picture. Measuring the slope, or the steepness of a straight line, that's simple. It's the same everywhere on the line. But our world isn't made of straight lines, is it? It's full of curves, company profits that rise and fall, the path of a ball through the air. And for those things, the slope is changing all the time.
So that brings us to the big question. How on earth do you measure the steepness of a curve at one single specific point? I mean, it seems kind of impossible, doesn't it? Well, the solution is just an incredible invention. It's called the derivative. You can think of the derivative as a brand new function whose only job is to be a slope finder for the original curve. You'll often see it written as dy over dx, which is just a fancy way of saying a tiny little change in y for a tiny little change in x.
So, how do we actually find this magical new function? Well, the original method has this simple, totally genius idea at its core. It says, look, if you can't measure the slope at one point, then don't.
Instead, what you do is you start by drawing a straight line that connects two different points on the curve. That's easy enough, and then you just find the slope of that simple straight line.
Now, this is the brilliant part. You take those 2 points, and you start sliding them closer and closer together, closer and closer, until the gap between them is practically zero. And as that gap shrinks, the line pivots until it's just perfectly kissing the curve at a single spot. It becomes what we call a tangent line, and bam, its slope is the exact gradient at that one single point. Now, that whole zooming in idea is the foundation of everything. But actually doing the math that way every single time is, well, it's the long way around, it's complicated, so thankfully, mathematicians develop some amazing shortcuts. And for most of the functions you'll see, there's a really simple trick called the power rule. Let's try it with, say, y equals 2x cubed. Step 1. You take the power, that's the 3, and you bring it down to multiply by the number in front. So, 3 times 2, that gives us 6. Step 2, you just reduce that original power by 1, so 3 minus 1 is 2. And that's it. The derivative is 6x squared. It's a brand new formula that can tell us the slope anywhere on our original curve.
Okay, so we've got this seriously powerful tool now. We can take almost any curve and find its exact steepness at any point, instantly. But, so what? What's the real-world payoff here? Why does this matter so much?
Well, the crucial insight, the thing that makes this so useful, is that for so many problems, the most important, the most interesting value the derivative can possibly have is 0. Just think about it for a second. When you throw a ball up in the air, right at the very peak of its flight, it stops going up, but it hasn't started coming down yet. For that one split second, it's perfectly flat. Same thing at the bottom of a valley. At these maximum and minimum points, the slope, the gradient, is exactly 0.
And right there, that's the ultimate power of differentiation. It gives us a precise way to hunt down the peaks and the troughs, the absolute best or the absolute worst points of any system we can write an equation for. This whole idea is called optimization.
Let's make this real. Here's a scenario from our source material. Imagine a chemical process where the cost, we'll call it C, depends on the temperature, T, and it all follows that function you see there. The goal is pretty simple. We want to find the temperature that makes this whole thing as cheap as possible. So instead of just guessing and checking different temperatures, we can be way more clever. We just find the derivative of that cost function, we set that new derivative to equal 0, and then we solve it. That will literally pinpoint the exact temperature that lands us at the very bottom of that cost curve.
And look at the result. It's incredible. The math tells us with absolute certainty that the optimal temperature is precisely 44.7 degrees Celsius.
And at that temperature, the cost hits its absolute minimum of £20.94. No guesswork, just a perfect answer.
This right here is the core of optimization. And this exact same idea is used everywhere. I mean, everywhere. Engineers use it to design the lightest, strongest materials. Economists use it to maximize profit. It's even at the very heart of how machine learning works, by constantly trying to minimize its own errors.
So, the real takeaway is this. Differentiation is so much more than just a tool for math class. It's the language we use to describe and calculate change as it's happening. It gives us the power to find the best, the worst, and the most efficient points in the world around us. Which kind of leaves us with one last thought. If you had this power to perfectly optimize just one thing, what would you choose?